Hi, today I'm going to show you how to use the PERT process for forward and backward computation of a network. When you're working with PERT, you have triple time estimates for each activity. So here we have a project with 6 activities. The shortest time to do each of these activities is recorded in this A column. This is the best case scenario or the optimistic time. Then you have the most likely or the most probable time estimate, and then you have the longest time that the activity might take, or the worst case scenario or the pessimistic time. Your book says that you can average these activity times. The formula given is T is equal to A plus 4M plus B divided by 6. This 6 will always be there for any problem that you work for and for all activities. The reason is the coefficients of A and M and B, the coefficients are 6, and so this is a weighted average that you're dividing by 6. So to compute the average activity time for activity A, we take 1 plus 4 times 3 plus 5 divided by 6. That's 18 divided by 6, so that's 3. So I will record 3 in here. For activity B, we have 6 plus 4 times 7 plus 9 over 6, and that gives me a 7.2 average. So I will record that here. Going down the line, I have 8.3, 20, 7, and 2.2 as average times. Keep in mind 2 things. Number 1, you don't want to round off the 7.2 or the 8.3 or the 2.2, because ultimately for each activity you round off their expected time or average time. By the end of the project, there will be some inaccuracies built into it. Also note one more thing. For those activities where the A, the M, and the B are equal distance apart, the average or the expected value will always be that middle value. For example, activity A is 1, M is 3. This is for activity A. A is 1, M is 3, and B is 5. 1 and 3 are 2 units apart, 3 and 5 are 2 units apart, so the average is going to be that. But for activity B, we have 6, 7, and 9. This distance and this distance are not equal, so you cannot use that rule, and you have to use this formula for activity B. Alright, once you have all of this done, then we can calculate the variance. Now remember, each of these activities are considered or are treated as a random variable. They can take on different values, and therefore we can compute an expected value for it and a measure of variation. So we can compute the variance for each activity so that later on we can use it in computing standard deviation for the project. Here's what the book says. Sigma squared for any activity is the range of the time for it, B minus A, the maximum minus the minimum, the range, squared divided by 6 squared. Another way of writing this, I think your book may have written it as B minus A over 6, that whole thing squared, but you can write it like this. And of course this means B minus A squared over 36. This is the format that I want you to use, because it keeps the 36 in the denominator and you don't have to keep using decimals and rounding off numbers. Let me show you. Here, B minus A for activity A is 4, so 4 squared is 16 over 36 is my variance. 9 minus 6 is 3, 3 squared is 9 over 36. 9 over 36 is the variance. Here, 6 is the difference, 36 over 36. Here, 20 is the difference, so 20 squared is 400, so we have 400 over 36. Here we have 8 minus 6, that's 2, 2 squared is 4 over 36, and here we have 9 over 36. We're going to use these numbers later on when we compute the standard deviation of the critical path. But now we want to use these average time estimates in our network. Let's assume for that network, for that project, we have this network. So going along again with this key where I write across the top of it early start, early finish, latest start, latest finish, and I have recorded the average activity times in here. I'm going to work the network forward and backward. So we have 0, 3, 0, 7.2. Here we take the largest of the two, so we put 7.2 plus 8.3, that's 15.5. Here we use 15.5 plus 20, that's 35.5. Here we use 15.5 plus 7, that's 22.5. And here again we take the largest of the two, so we get 35.5 plus 2.2, we get 37.7. Now working it backward, we put the 37.7 and we subtract the 2.2 from it, so we get 35.5. Now let's examine these. This is the earliest finish time for the project, but remember these were average times that went into calculating this project. So this is really the average earliest time that we can finish this project, and this is the average latest finish time that we can finish this project. So all of these times are averages, essentially, or expected values. Now, working it backwards, we put the 35.5 as the LF, subtract 7 from it to get 28.5. Do the same here, subtract 20 from it to get 15.5. Working backwards, when you work backwards for, and there are two numbers to choose from, you always, in the backward pass, you pick the lower number. So we put 15.5, subtract 8.3 from it to get 7.2. The reason for that is because C must accommodate both D and E. At the latest, D must start in week 15.5. At the latest, E must start in week 28.5. But because C must accommodate both of them, we pick the lower number. And finally, we get 7.2, subtract from it, we get 0, and we get 7.2, subtract 4 from it, and we get 4.2. So the critical path can be computed by, or can be found by computing slack. Here we have 4.2 as slack. Here we have 0. Here we have 0. Here we have 0. 13 and 0. And of course you compute slack by taking LF minus EF or taking LS minus ES. I recommend that you do both of these computations, because if in your forward and backward pass, when you have more than one number to choose from, if you made a mistake, it's going to show its face in these computations, and these two numbers would not be equal to each other. So you want to always double check yourself. So this is the critical, this is the network. The critical path is B, C, D, F. Notice that the time for B plus time for C plus time for D plus time for F, which are the critical activities, which is the 7.2 plus 8.3 plus 20 plus 2.2, gives us the 37.7, which is the average duration for this project. Now what we're saying is that this project on the average takes 37.7 days, weeks, I can't remember now what I said, but let's say 37.7 weeks to finish. Now 37.7 weeks is the average completion time for this project. That means that there's a 50% chance that the project will take less than 37.7 weeks, and there is 50% chance that the project will take longer than 37.7 weeks. So as with any random variable, if we know the expected value, we should also be able to compute the standard deviation for it. So the standard deviation for this project is what we're looking for. Now, the critical path, remember, was B, C, D, and F. To compute the time for the critical path, remember we added the expected value of all the critical activities. So to compute the sigma squared for the critical path, we add up the sigma squared for activity B, sigma squared for C, sigma squared for D, and sigma squared for F. Sigma squared for these activities, remember we recorded them. B was 9 over 36, C 36 over 36, D was 400 over 36, and F was 9 over 36. So if we compute all of those, we get 400 plus 18 plus 36 divided by, which is 454 over 36, because we have common denominator, divided by 36, we get 12.61. Now, that's the standard that's the variance for the critical path. If we take square root of the variance, we get 3.55. So I'm going to round that off to 3.6. Remember, the 12.61 is variance, and that's in weeks squared. But the standard deviation for the project, for the critical path, is 3.6. Two things to consider. Number one, students often make this mistake. When they want to compute the variance, they add up all of these activities. You should not do that. You should only choose the critical activities, which in this problem they were B, C, D, and F. Point number two, sometimes students take each variance of the critical activities, take square root of them, essentially computing the standard deviation for each activity, and then they add it up. That would give you the wrong answer. That's not, mathematically, it's not the same answer. So what you need to do is you need to add up all the variances for the critical activities. Once you know the variance for the critical path, then you need to take square root of it and get the 3.6. So now we have a project which on the average takes 37.7 weeks on the x-axis, which is in weeks, and on the z-axis we know it's going to take the z-value is 0. So we can compute various probabilities. For example, what is the probability that x, or project time, is less than or equal to 40 weeks? That would be this area over here. Or we could say, what is the probability that project time will be anywhere between 35 to 45 weeks? And in that case, that would be this area over here. So we can use our normal curve knowledge to answer problems such as this. And this concludes our session on PERT. Thank you.